Hi, I'm Dr. Dow, and I want to talk about my heart pump today. This is a pulsatile heart pump versus axial flow units. This pulse unit right here is mainly a body emulator, and these tanks here just will show varying compliance on the pulmonary side and some of the peripheral vascular resistance side, and these gauges this show pressures in those variations. The valves here you can change, simulating varying physiologic conditions, and then we'll see how the pump can react to that, very much like the heart does. The key part here now is this pump chamber down here and the drive mechanism. It's got a titanium chamber back here, but then the drive mechanism is all enclosed right in this section right here, and it's a magnetic drive. So that's kind of new and kind of neat, and it has very few moving parts, and it should last a long time. Maybe up to 10 years, or at least that's what we think now. So if you watch this now, I'm going to turn this thing a little bit, and you'll be able to see right down in here, and you'll be able to see the diaphragm move just by changing the air pressure out here. I just want you to see that motion, okay? I'm going to put just a little pressure in these tanks here, and what you see right there is the pusher plate that's on that diaphragm. Now let me just watch it. See it come across there? All I'm doing is just putting a little pressure in the chamber back here to bring it across, okay? Now it's pretty much across. Now when I let the pressure out, it's just a normal action, it'll go back across. Well, as I turn these magnetic drives here, you watch them kind of push that back across there, okay? And now it's about all the way across. So that's the stroke of the pump, okay? We really don't need the motor to drive this right now. I'm just going to pull it out of the way, and then we'll see how this thing breaks down here, and really how simple it is. Let me get those out of the way. Now, we're ready. Let me turn it back around this way, and I think you can see all that's out of the way now, and I've got most of these screws out so we can disassemble it very readily. Let me take an Allen wrench, and I'll pull these two out, and then we'll be into it. Okay. Now, here's all we have. This just turns a drive shaft through here, comes right through here, and is attached to this plate. And this is an activator plate or an action plate. It's just got 4 big magnets on it, or large rare earth magnets, and they just rotate with the plate. And it's very simple. These larger magnets here have a little more force than these do. These are put on here to kind of lessen the recoil, or kind of control the recoil as the chamber is filling, okay? It's a better simulation of the heart as the heart fills. But this helps attenuate the forces that these may generate as they turn, and due to some of the magnetic fields that are generated there, even though these are repelling forces, they in a certain position they develop an attractive force, and these attenuate those forces. So this just turns very simply like that. And there's a thrust bearing down in here, and that's all there is to it. If you need, we'll pull that shaft out of there, and you can see, but it's real simple. I'll set it back here now for a minute. Now this right here is the pusher plate. Now see it slide in and out of there? You can even see the gauges move up here as I put a little air pressure on it there. And it's got these 2 big magnets. Like this is a south pole, this is south pole, and these are all south poles, and these are south poles, so they all repel each other. And as this turns, this is another feature here. This little shaft sticking out here and goes in this hole. That's a guide shaft, just to help keep alignment of these bearings and these forces as it pushes the pusher plate. As this turns like this, say right now, if it was sitting in here, this would have this in a repelled position like that. Now as this turns like to this position, then there's no forces here, no major forces, then this would come out for another stroke. And as this turns like this, then you'd have another pushing stroke or repelling stroke. So for each revolution here, you get 2 pulse units, or 2 pulse efforts, And basically that's all there is to it. It's just you spin this unit with a motor here, or you build your motor right into this section of the pump, and it just pulses back and forth. The main force here that keeps this torque that generates as you rotate this out of from being any kind of a problem is the diaphragm itself. And it's a rather simple diaphragm, but and right now it works great, you know, and the pump will generate at maybe up to 120 millimeters, 130 of systolic pressure, and it drops down to about 80 and 90, just like the heart, and it'll pump 55 or 60 cc's a stroke right now with these magnets. I'm really going to have to put a little bit bigger magnet, a little bit stronger in there to get this thing to pump maybe 90 to 100 cc's per stroke. But it should do it. You know, it should do it very easily. And as it does, though, it's going to generate a little bit more torque on this thing. Right now, this thing, this diaphragm handles that rotational torsion or torque very well. It just slides in and out like it should. You know, when we get up to 100 cc's, if we need a little more resistance with that rotational torque, my plan is to put a kind of a stria or a little belt effect or a little ply effect, incorporate that into the diaphragm, and just to give it a little added strength there, so that this thing, you know, this thing should run. With that in place, you know, the limiting factor will be how long the motor will last. The diaphragm should make millions and millions and millions of strokes, you know, maybe 400, 500 million strokes or more. The motor should last up to 10 years or longer, and all we've got a thrust bearing here, this little thrust bearing, and it should easily last that long. So that's what we're looking at, and these forces that are generated, we need to really mimic or emulate the human heart. I mean, that's the goal here. Axial flows, they can never do that. There's just no way. But you know, we've just got too much going on in the body that needs a pulse. I mean, in the brain and just lots of places. And we get into complications with axial flow units, with, you know, whatever, strokes and all kinds of embolies that form and things like that. And those are just those are risks that, you know, I myself just can't accept. And I think there's a lot of physicians out there just like me. We need a pulse that simulates our heart, and that's the goal here, is to emulate or simulate the heart in varying physiologic conditions. And you know, that means if you get up and run, or you sneeze, or you cough, or you go to bed, or whatever, your heart changes, and the volumes change, the pressures change. This thing changes just like that, okay? And it's the varying magnetic fields and the structures of them and how they approach and go away from each other that allows these plates, as they separate, to really emulate the contractile forces of the left ventricle. And you know, if we can do that and emulate or duplicate that pulse pressure wave, I mean, we're home free. That's really all there is to it. So that's been my effort here for the last several years, is to try to emulate the pulse pressure wave in the human in varying physiologic conditions, and this thing is getting real close. Okay, this is my pulse pump again, and I just want you to see it run a little bit and see some of the strokes and how it changes with varying conditions here, varying body conditions. Okay, I'm just going to turn it on here and let it run just a little bit, and you can see kind of how it gives us a pulse action. And you can see, I don't know if you can see the valves working here, but like this is the inlet valve and that's the outlet valve back here. And right now I don't have any resistance on this, sort of just free flowing. I'm going to change these parameters here a little bit with the pressures. And you watch that action there. I'm going to speed it up just a little bit. Watch that as I increase the filling pressure here, and Just watch it, see it, it'll come right on back, and the stroke will increase. There, we're back to almost a full stroke now. I'm going to put a little bit more pressure in it now, and we'll see those. You'll see this change here more. Come back. Those magnets will approximate themselves closer, and the pressures will get higher, and the valves will work a little harder as the pressure comes up. See, now it doesn't have a real large stroke, but the pressures have come on up to, looks like about 130 over maybe 70, 75 now, maybe 80. It just keeps climbing a little bit. Now we're going to let a little pressure off there, a little infilling pressure, and you can watch that pump go working right back across to the other side of the stroke panel. We're within the range of the left ventricular musculature right now as far as contractile forces, so I don't think there's going to be any problem in getting real close to duplicating the forces of the heart here.